Okay, hi, good afternoon, Bob. How are you?
I'm very good, in the
I,
right place as always.
yep, I can see that you're in the right place. Hey, Bob, listen, I wanted to pick up on a couple of things which I think are pretty interesting here. 10 years ago now, the New Scientist picked up on an article about some foundational thinking you'd been doing with respect to natural language processing and the quantum computing paradigm. And then over a year ago, 9 years after that, you went into deep stealth mode with some projects to do with implementation. And then 5 months ago now, just over 5 months ago, Bob, we had our first quantum natural language processing conference. 2 weeks ago, you announced to the world that you and your team had implemented for the first time such let's call it an algorithm and a protocol on an actual quantum computer. You published an article on it. And now, just this last week, you've issued two papers. One of them is quantum natural language processing on near-term computers. And secondly, you and your team have come up with DiscoP, which is monoidal categories in Python. There's a lot of momentum here. And my first question is, why does this matter? Why should people care about natural language processing and quantum computers?
To explain this, I'm actually going back to where you started, which is 10 years ago. We were dealing with a problem which was communicated to us by a leading computational linguist who ended up actually on the first paper, Steve Clark. And they said, we really don't know in NLP, when we know the meanings of a word, how to turn them in the meaning of a language. I mean, the idea is if you type in a few words in Google, and when they form a sentence, Google doesn't get it as a sentence. It gets it as a bunch of words. It takes some structure into account, like order, but it doesn't get it as a sentence. So the problem we tried to solve then was, basically, how do we do that in the first place? How do we produce the meaning of a sentence we've never heard before, provided we understand the words it's made up from? So if we hear a sentence we never heard before, we do understand it, provided we understand the words. So how do we do that? What is the algorithm or whatever we use in our head? And how can we turn this in an algorithm that Google then can use, or whatever NLP task? So we started doing that. And I mean, it wasn't really too difficult. We looked at the structure of language, and then we observed that the structure of language was pretty much exactly the same as the structure which people in NLP had been using to represent meaning spaces. Well, actually, how meaning spaces are organized when you stick them in what is called a monoidal category. So basically, you had the same structures. We could just translate grammatical structures on these meanings. Now, what does that mean? And what we realized at the time is that the structure we had there was exactly the same structure as I had been using for more than 10 years, almost now 16, 17 years, to formulate quantum mechanics. Exactly the same structure governing quantum mechanics is exactly the same structure governing language, is exactly the same structure governing the category of the spaces people are using in NLP. So it all perfectly fits together. Now, at the time, we were using the quantum aspect just as inspiration. And this was a very good inspiration to actually push the field of doing NLP, taking into account compositional structure. Now, the downside of doing all of that was that it turned out to be exponentially expensive. And that's why people are not really using it in NLP classically at the moment, because it's not straightforward to do it. It's exponentially expensive. Why is it exponentially expensive? Because it is quantum native. What do I mean by quantum native? By quantum native, I exactly mean what Feynman intended it to mean, which was that if you're going to stick quantum calculations on a computer, then you're better off having a quantum computer, because quantum stuff wants to be computed on quantum stuff, not on classical stuff. Same is true for this stuff. Language structure wants to be computed on a quantum computer. On a classical computer, it's exponentially expensive. And that's why people in NLP find it actually easier to let the thing be learned to whatever is needed, rather than actually sticking the entire language structure in. At the time, we were really, I mean, we did some experiments classically and they outperformed everything existing. It was just hard to scale. Now, quantum computers got a bit better. And after 10 years of saying, yeah, we never intended this to be quantum, we can actually say, actually, it always was going to be quantum at some point.
Thank you. It's exciting. There seems to be some momentum here. And can you explain the timing of the first paper? Because my recollection, and I was one of the lucky ones to be at this seminar and the conference that we had in Oxford, but it seems to me that the paper that you've produced with Konstantinos, Stefano, Giovanni, Nicolo, Alexis is actually an expansion or an extrapolation of the work that was presented at that conference. Is that right? And could people look at this paper in conjunction with the videos from that conference?
I mean, to some extent, it's the write-down of what was indicated there with a little bit more digestion. That's exactly that. So basically what happened is, like, a few years ago, with somebody who's now quite well known in the quantum business community, Will Zhang, we basically wrote down why this language stuff should actually better fit on a quantum computer. So we made a few points. First of all, there was, of course, the case that it looked like quantum, and basically the spaces you need to do that stuff scale exponentially. So on a quantum computer, they wouldn't scale at all. They would just be linear. So that's a big upshot. We had been working with things like density matrices already in the classical world, which are things which are, again, natively quantum. They are things which you get for free, quantum. And then we also figured out that you could use a bunch of quantum algorithm, quantum machine learning algorithm, to, on top of all of that, speed up things beyond what you would expect classically. What this first paper does, you mentioned, is actually filling in the blanks there, and also filling in what turned out to be a bug. Not really a bug, but so in human language, you can't just take classical linguistic data and stick it on a quantum computer naively. It doesn't work. It would only work if there exists some quantum analog to RAM, classical RAM, random access memory. And it's even unlikely, or, I mean, I'm not a specialist there, that such a thing will exist in the near term. So you have to come up with another way to get your data on a quantum computing. And there we discovered that there is another big upshot, like the way people had been encoding data on a quantum computer in a feasible way that you don't lose too much, which is partly was done at CQC by Marcello, was to use circuits, and then you use some tweaks and variational circuits. So it's machine learning, AI. And in that way, you can actually, in a decent way, get data on a quantum computer. Now, what is a huge upshot for the qNLP is that these people, like Marcello, constrained by the architecture of a quantum computer, have to sort of assume that everything takes the form of a circuit, which is a big compromise, which is something you have to live with. You have to squeeze whatever you do within the form of a circuit without any justification. What you see here on the left-hand side is the diagrammatic language of grammar. And you can actually topologically deform this into a quantum circuit. And that's exactly what we did. So the circuits actually embody grammatical structure. They are not a compromise, they're a feature. They're a feature, not a bug, they're a feature. They capture the quantum native grammatical structure. So basically, even as a quantum machine learning paradigm, this is a big upshot. This is a very big upshot. To have these circuits now means something.
As maybe a closing point for now, and as you say, this is very exciting. What can we expect next? What have you and your team got in store for us as we go forward? And as you answer that question, the other thing I'd like, if you can briefly, just for whoever's listening, remind us of why the work on monoidal categories might have a broader impact than just on natural language.
Well, to some extent, they have the same question for me. So yes, use the word monoidal category. By that, we refer to all these diagrammatic structures, like these linguistic structures, the the circuits you saw, and also quantum mechanics as written down in this book. So this is all monoidal category, is all compositional structure. I mean, it's my belief, and this is like a scientific, like a deep scientific foundational belief, that is the most primal structure in the world. That that everything pretty much is a monoidal category, and that instead of counting, which is how mathematics pretty much started, it should have started with monoidal category. Like, I mean, we had Euclid, geometry, he did the right thing. He had his points and his lines, and he was thinking about intersection and composing. That was like a beautiful way to set up mathematics. For me, it should really be about the things you care about, the way they can change, and how all simple things then can make up big complex things. Like in terms of cooking, this would be, what are your ingredients? How can you process them? And how can you turn this process in a full recipe? For a computer, this, what is your data? How can you process data? What are your programs? And how can you turn modules, little modules in your program, into a big useful application? Same is true with physics. What are your systems? How do they evolve? And how do they interact? And that's exactly where all these coinciding diagrams come out. And so part of the qNLP stuff, the machinery in that first paper, is a thing done by Alexis and Giovanni, which is Discopai, which you mentioned. And we used it to do the translation between the two diagrams I showed. But this is just toolbox to deal with monoidal categories, with everything I was mentioning. So it's a toolbox where you can deal, when you think of the world in these terms, monoidal categories, then this is your toolbox you're going to build stuff with. That's what it is. So it's a very general thing. It's a very general thing. But altogether, what the next step is to take this qNLP and put more generality like that in it. Well, we want to, of course, scale up to much more complex linguistic talks. I mean, I've been only showing sentences so far, but actually we can deal with entire text, We can deal with evolving meanings, which is very like meaning update, which means we can also deal with like agents, representations of the world and things like that. And we also want to go beyond language, which we did already before in a theoretical way, to other cognitive modes, other way of reasoning. Ultimately, this could become some general compositional AI. I mean, I'm thinking really big, because I also think that the problem of language, the composition, which is exponentially expensive on a classical computer, is gonna be the case for all of AI if you want to do it properly.
Bob, I think on that note, we might just bring this brief conversation to a halt. So if I've got this right, for people who are maybe listening to this for the first time and who've got an interest either in quantum computing or machine learning on a quantum computer, or indeed in language processing, you would suggest maybe watching the videos from the conference, then maybe having a look at the Medium post that you guys put out a couple of weeks ago, and then these papers, in that order.
I mean, maybe before the papers, I would look at maybe my MIT talk.
Yes, and that as well. Yep. How could I forget that? Yep. Great. Thank you, Bob, so much. That's wonderful.
Thank you, Ilyas.
Take care.